Okay, so the next half of this course is going to focus, the next part of this course is going to focus on cloud security. And before we talk about cloud security, I want to just give a brief overview of the cloud. Like, why is it important that we're learning about these things? I don't have to motivate it as much now as I used to, but up until now, we have focused mostly on web application vulnerabilities, application security, but the vast majority of the web applications are actually hosted on public cloud providers like AWS, Azure, and Google Cloud Platform. And typically, when an adversary compromises a web application, then what they're going to do is look to pivot from that web app to wherever else they can get access to in that backend cloud project. This is called lateral movement. So MITRE has this attack framework, and there's like 8 steps that an adversary will do to get full-on data exfiltration. Lateral movement is like number 4. Like, the initial vulnerability leveraging is like step 1. Now, actually, information scanning is step 1, and then the actual leverage of an application is step 2, for example. The most famous example of this is a Capital One breach. There was a web application that had an SSRF vulnerability that you now are very familiar with, and then that allowed a full compromise of the AWS storage buckets on the back end of Capital One. Okay, so there is this mass migration of businesses to the cloud underway. A lot of companies are moving to it. The software and the services that people are developing are being migrated onto it. If any of you are in internships, how many of you are in internships that don't use the cloud, a cloud provider? All right, so for those watching at home, that is no hand was raised. So they're like, you go out in the job market and they're like, oh yeah, this is on some AWS instance, or some people are using Google Cloud, yeah.
I work for a company that does archiving,
and
we are working our way. We're migrating.
You're okay. Your company's on your way, all right.
Part of it.
Okay, it's a mess. Okay, yeah. Okay, if Multnomah County is putting stuff on the cloud, yeah, they're not an edge leader there in the discipline.
On the other hand, we get a lot of pushback from clients that don't want their stuff in the cloud.
Yes, and the reason why clients are pushing back, they don't want their stuff on the cloud, is because it's hard to secure stuff on the cloud, which is why we have this nice 3-week exploration into how do you lock things down in the cloud. Because if you look, there's a lot of companies that are like, put your stuff in the cloud because of X, Y, and Z benefits. But like downside risks, nobody wants to talk about downside risks. If you're trying to make money as a cloud provider, you wouldn't talk about the downside risks very much. So we're going to talk about the downside risks because actually, as an engineer, you can make money understanding how to minimize the downside risks, because $9.5 billion that Equifax is going to have to pay is going to motivate hiring people who actually have some understanding of how to configure things in the cloud. Just saying. Okay, so why are people doing this? The big motivation is that you can go assetless. Your company no longer has to buy hardware, no longer has to configure software, no longer has to hire people to do all of that stuff. So that's the big reason. You can have the ability to pay for only what you use, right? If I need 10 servers today, I'll allocate the 10, but then all of a sudden, if my user base shrinks, maybe get cut in half, I can go back down to 5. So that's a big benefit. You can get rid of a lot of IT people, IT and ops people, actually. So a lot of the older tasks, well, not older, but a lot of the tasks in deployment and maintenance of infrastructure, it's handled by software by a cloud provider. You basically automated away a bunch of jobs that we used to be training people for 20 years ago. 20 years ago, where it's all about IT management and managing machines, a lot of that stuff is going away. And the big reason, so the reason why companies are looking at this is now you can have, for the first time, you can have an exponential increase in the number of machines that you deploy without an exponential increase in the number of engineers that you have to hire to manage those machines. So that's one of the biggest reasons to move to the cloud. And then there's a utopia of lots of amazing services in the cloud. So if you've taken the cloud course, some of these things like the ML APIs, this is how Google is getting a bunch of people to use their platform. There's GIS and mapping APIs that a lot of people use. There's data warehousing that's there. So a lot of these things are available in the cloud. And so if you want some visibility into a bunch of different things in other people's sort of APIs and your own, you would move stuff to the cloud. Okay. So that's the spiel on motivating it. I'm going to now give an overview of the kinds of things that are being deployed in the cloud. I'm going to sort of group these into 3 areas. The first thing is server-based infrastructure. The next thing is serverless applications. And then the last thing is services themselves. We'll start with the first class, which is server-based infrastructure. And one of the things that I should note here is that when I talk about these classes of resources, I'm going to give you what you need to make sense of the exercises that you're going to do. I'm not going to give you everything in the cloud. That would just like completely overwhelm you. But in order for you to really understand what you're doing when we do these exercises, I want to give you the bare minimum. So this is the bare minimum sort of intro to cloud services. We'll start with server-based infrastructure. So the first class of infrastructure, this is considered what we consider legacy infrastructure. So we come from an age where people have a server that they deploy, and that server contains whatever resource needs to be served. And so we have this machine model, right? A resource per machine. And if you have that model and you want to move to the cloud, the equivalent service in the cloud would be infrastructure as a service. So you've been using this for Compute Engine, and we'll see this for EC2. All these things are virtual machines on demand. Okay? This is considered the lowest level abstraction in the cloud. And it's good for arbitrary workloads, right? You're not constrained with any software stack. You can build your own software stack and deploy it on these things. But the big disadvantage is that you still need manual management by the developer. Someone has to manage the software stack on the virtual machine. You don't have to pay anyone to manage the hardware, but the software stack is still something that you have to keep up to date. And so one of the things that these IaaS services allow you to do are things like performing disk snapshots or backups, and this will come into play in flaws.cloud. It allows you to produce machine images, and these are the machine images that you were using for the Web for Pen Tester sets of labs. It's important if you do have secret information in either the snapshot or the image, it's important that you lock that thing down. And so we'll see in both of in flaws.cloud, if you fail to lock down a disk snapshot, then someone is able to access that snapshot and pull the secrets out of it. So that's the idea there. Another class of server-based infrastructure are just simple database servers. So Google Cloud has this Cloud SQL service, and Amazon has their relational database service. And these are basically virtual machines that come pre-installed with the database software that you want to run on them. So it semi-automates some of the installation of the database software, but it's basically a virtual machine. You say that there is actually an IP address for that database server that is exported to you. Okay. And these are drop-in replacements for any legacy app that is pointing itself to back-end SQL, like MySQL or PostgreSQL, or Microsoft SQL, any of these relational database backends that are for applications that were written in the 90s. And some stuff is still written to them now. The way you access these database servers is typical username and password. So you'll see something like this. You won't see something like this. Oh, I'll show you this later. The third class of server-based infrastructure are containers running on servers. So what are containers? If you haven't taken any of the operating system or cloud classes that talk about containers, containers are basically virtual operating systems. You have virtual machines that virtualize the hardware. Containers are virtual operating systems. You have one underlying operating system, and it's supporting the ability to load multiple virtual operating systems on top of it. And this is typically mapped. You're running these virtual operating systems on an actual operating system kernel, which is actually mapped to a virtual machine that you explicitly access. Okay? So the de facto standard is Docker. And so this is a picture of what Docker does. Docker has a single operating system kernel, and then these virtual operating systems, these are basically, each one of these containers is basically a separate namespace in the underlying kernel, and each container contains all of the container-specific software needed to run on that version of the kernel. So if you see on the left, this is a Java-based container using Debian, and then running Tomcat, which is a web application server, running on the same kernel as a SQL Server.NET with Ubuntu libraries. And the way this is supported is underneath all of the kernel libraries that the Ubuntu and the Debian share are provided in the underlying real operating system. And then there's a namespace to fake the applications up above that make the application think that it's got a dedicated operating system underneath. This is much more efficient than doing virtual machines, because in virtual machines, you're replicating all of this from machine to machine. Okay? So containers are run using from pre-built container images. And these images are stored in registries. So the most common container image registry that you'll come across is Docker Hub. So whenever you see a URL with docker.io, this is pointing to Docker's container registry. This is a public registry for container images, and you can consider it GitHub, but for container images. You will also, in your exercises, be using the Google Container Registry and the AWS Elastic Container Registry. These are private container registries local to a project, right? Like if I have a container that I'm running all of my secret infrastructure on, I don't want that on Docker Hub, right? And I don't want to download it from Docker Hub. I don't know what kind of network connection Docker Hub has. When I start up a container on my project, I want it to be fast, and I don't want anyone else to see it. And so that's why GCR.io and ECR.io exist. You get your own separate registry for your project, dedicated for your project when you create your project. That's the idea of these two things. Okay? So private container registries that function exactly the same way Docker Hub functions. So the UI is the same, you just give it a different URI. This is what it looks like. You have some kind of registry here. It's got all the images you want to run. When you instantiate a virtual machine, you will pull the image that you want to run onto that virtual machine, and then you will run it. And then from that image, you will have, at runtime, any number of containers running on that computer. And these are the commands that you would run. Okay. The thing about container images is that they are built for efficiency. Containers and container images. So if you want to have a container ecosystem and you don't want it to completely blow up, then the way Docker has organized the images is to organize them in individual layers. And each container image can consist of, at most, 128 layers. But the thing is that if there are containers that share layers, you only have to store that layer once. And then both containers can use that layer when you download it. Okay, so the Docker runtime only stores the layers that are unique to the container image. So here's an example. If you have a Docker file, and Docker files are recipes for building container images, and each line of a Docker file is a layer in the container image. And so here's a picture, and it's an awful picture, but it's the only one I could find that was really nice. Starts with a Ubuntu base layer, and then runs this command, add this file to the container image, run this command onto this container image, run this command on this container image. And you see that each of the individual commands end up with a particular image layer that gets added onto the base layer. And then at the very end of this, these layers are combined into that container image, and then you can run from there. Okay, the big thing with container images is that if you do have secrets in them, you have to make sure that image is secure, like it's protected against access. And so you'll see this show up in Thunder CTF. If a developer has put a secret inside the image and has allowed that image to be viewed by an adversary. So say you compromise a web application and you see the web server has access to the container registry. You can then scan the container registry for all the infrastructure container images that project runs and find anything that exposes a secret and then go and pivot to that whatever machine is running that container. Okay, so that's why it's important. Are there questions about that? Okay. So we talked about 3 different things. The next thing is serverless applications. So what is serverless? I define serverless as a solution that costs nothing if nobody is using it. No upfront provisioning, no runtime management of servers, and you pay for what you use. So when we talk about server-based infrastructure, someone has to manage the software stack to keep it up to date. When you talk about serverless, there are no machines to manage. There is no software stack to manage. That's the whole point. I don't have a server to get my hands on. So that's what a serverless application is. So the model is that the developer just produces code, right? And if you're on the dev side and you could care less about the ops side, then yeah, you want a serverless infrastructure. You want a serverless application to build because I don't want I don't want to know about IP addresses. I don't want to know about security groups, firewall rules. I don't want any of that stuff. I just want my app, and I want my app to work and scale up and down on demand. Then you want serverless. Okay, so this is what a lot of people want to move to. Unfortunately, we have decades worth of older stuff that is not serverless. So that's the model. You produce the application, and then the infrastructure will just run it. So it's serverless in that the developer doesn't see the servers, or they shouldn't see the servers. It should run without you seeing that. Okay, so it's all hidden. It's not exposed. I mean, there are actually servers there running your stuff, but the idea is that it's supposed to be hidden from the developer. Okay, so the benefits of serverless: avoid the infrastructure costs up front and the rapid depreciation. So yeah, when you buy a server rack, almost immediately it starts to depreciate in value. So as a company, you don't want that on your books, right? You just want to you want a reliable expenditure that's based on a serverless usage is the idea. Okay, the other thing is that you can focus on your core competency, like your app, rather than infrastructure management, which is not your core competency typically. You have to actually hire someone, and you don't even know who to hire, right? Like how does an app developer know what kind of ops person to hire? It's completely separate. So different disciplines, I should say. Okay. The other benefit is that it might be more secure, right? There's no machine or network to configure, so there's no persistent machine for an adversary to get onto to pivot over to any of the resources that you might be trying to protect. Okay, I put this question mark because this is to be determined, because serverless hasn't been around long enough to be attacked as much as the server-based stuff has been. And actually, one of the exercises will be attacking a serverless application. So this is, I didn't want to make a snap judgment on that one. Okay, so I'm going to talk about the 2 different kinds of serverless deployments. Actually, we're only going to do one, but I figured I'd give you at least more than one to talk about. The first kind of serverless infrastructure is the serverless platform. So 2 examples are Google's App Engine and AWS's Elastic Beanstalk. So the idea of these 2 services is that the provider gives you a development environment. So for example, a Node.js environment, or a Python environment, a Python 3 environment. And then what you do is the app the developer produces an app and then sends it to the platform, an entire app, and then the runtime just runs the app. What it'll actually do is it'll automatically containerize your app and then deploy it on nodes in the cloud. And the benefit of this is that there's actually no need to deploy virtual machines, and there's no need to construct your own Docker image, your own Docker file, right? It's just an app. The Docker container is actually being built underneath in this platform. Okay, and then the cloud provider, App Engine, or Beanstalk will deploy that app to any of the actual VMs underneath. And then the platform is managing the networking, the patching, the load balancing, the monitoring, the versioning, and the backups. All that stuff that you really don't want to have to pay attention to as a developer, the platform is going to pay attention to that. Okay. So the actual machines and the containers that implement this service are completely abstracted out. The other thing that, the main thing that we're going to come across are serverless functions. So Google Cloud Functions and AWS Lambda. And these are special cases of platform as a service, but instead of running your entire app, these things are intended to run a single function that you define. So a function call in your programming language environment is the abstraction that you provide that this Lambda or this cloud function is going to execute. These functions are run on ephemeral, predefined, time-limited runtime systems. So time-limited in that you're not allowed to execute more than a handful of minutes for each function. So you don't want to have a long-running application as a Lambda because it'll get automatically shut down. If your serverless function is super popular, then the runtime is going to scale up and down the number of back-end servers that are going to be used to process that. Okay? These functions are typically stateless, but if you need these functions to store state, you'll often point them to back-end services that actually, like maybe storage buckets or databases that will store the actual state that you need from request to request. Okay, so you will see that serverless functions are often used to implement REST APIs. So we talked a little bit about REST APIs. There are two ways that you'll come across REST APIs being implemented in these exercises. The first is Google, on Google Cloud Platform. Cloud functions can be defined with HTTP triggers, and those things are basically allowing you to implement the REST API because the function needs to handle HTTP, so that's what this is used for. On AWS Lambda, you can associate a Lambda to Amazon's API gateway. And then the API gateway has an HTTP sort of route that you would hook the two things together. So that's how that works. So the cloud function with HTTP triggers, that's going to be used in the Google CTF I'm going to have you do. And then the API gateway is going to get hit by this serverless goat exercise that I'm going to have you do. Okay, so the third piece of that, so you have server-based stuff, serverless apps. The third thing is services and APIs. So these things are just fully managed services that your application can just use. And then whoever is providing that service manages everything. Now you don't get to run code on their stuff or anything like that. It's just they're exporting you a service and then you just use it. The first one that you'll probably come across a lot is cloud storage. So Google Cloud Storage, and then in Amazon, it's Simple Storage Service, S3. These are storage services that the provider manages. And these things are automatically backed up, versioned, replicated, and cached. They're also forward deployed to the locations in the world that it's being accessed from. So you can have these settings where it will actually act like a content distribution network and then forward deploy the nodes. And the important thing here is that the actual physical node that is handling this is decoupled from the URI that you access the object. So rather than in most URLs, if you bind the resource that you're accessing to the actual physical node that implements it, you are stuck. You can't scale that thing up. What S3 and GCS do is that there is a logical URL that's being implemented, But the disks that implement that thing, it could be replicated everywhere in the country or in the world. So that's what this service, there's a lot going on underneath these services, but that's the reason why these things exist. Okay. So the buckets, well, the storage is done using this bucket abstraction. So they're like URLs, but they're just basically unique identifiers. So when you have a bucket name, it doesn't reveal where the actual storage is happening. It's just an identifier. When you have a bucket and you want to access something in it, it's done using an object abstraction, much like URLs, right? It's not like, hey, I want this number of bytes from this location on disk. It's like, hey, I have an identifier. I have an image that I want to get, and then the storage bucket will give you the entire image. Okay, so that's what we mean by object-level storage. Okay. The other kind of service, and we already talked about databases, but these kinds of database services are different. So in the previous one, when we talk about databases running on virtual machines, you have fixed the virtual machine and the location of that database. Database services are done completely serverlessly. You don't know where that data actually gets stored. You just write to an API that the cloud provider provides, and it's going to store your data, and it's going to replicate it, and it's going to distribute the workload across any number of machines on the back end. So there are two kinds of these serverless databases. The first is the NoSQL databases. And so Google Cloud, Cloud Data Store on Google and AWS DynamoDB are two database services that implement this NoSQL data backend. And these are basic schemaless. So NoSQL is basically a schemaless data store. So you specify a key, and then you give it an object, and it could be any number of types. So it's completely auto-scaled and managed for you. There's no configuration. And then they support programmatic access and insertion into these backends using a REST API. The last one I want to talk about is data warehouses. And the reason why I need to talk about this one is that you're going to be using Amazon Athena for one of your exercises, the Flaws 2 Defender path. So what are these things? If you have a massive amount of data, then typically you have to store all that data on disk. And so what BigQuery and Athena are doing is trying to give you query infrastructure on top of disk storage that's flat. So both of these data warehousing solutions are for querying log data. It's often used for querying log data. And as it turns out, querying log data is what you have to have for cloud security. So if you're trying to attribute the source of a compromise, what you'll end up doing is going back and running queries on some backend that has stored all of your log information. Not necessarily Athena, but like I think we mentioned before all these other different kinds of services for doing logging. Those would be the things you would run. Okay. So this brings us to logging. Both cloud platforms allow you to take all of your log entries. Yes? Yeah, so the Elasticsearch, the log, yeah. So that's the ELK stack is basically taking log information, the log stash, putting it into a search format, and then the Kibana is querying it. So that's one instance of that. You could do something similar by pushing it into BigQuery and then running BigQuery queries on top of your log data. So different kinds of, you could do whatever your I guess your operation is using, you would fit this in, but it's the same idea. Yeah. Okay. So in terms of logging, typically what happens in the cloud, if you have serverless applications, you need the log files to be stored somewhere, right? For server applications, you just store it in the log files on that server and then you go and retrieve it. But if you're trying to integrate the logging across your server-based infrastructure, your serverless infrastructure, along with the API accesses in your cloud project, you need one integrated sort of solution for storing all your log entries. That's what Stackdriver is, and that's what something like CloudWatch does. It allows you to have this single sync for all your log data. And this is similar to a seam, the sort of the seam stuff that we talked about last time. Okay, so the idea is to log every single action and that's going on in your project, and making sure when you do that logging that nobody can go in there and modify it, right? Making sure that it's append only and that someone can't go in and delete the log files to cover their traces. So what's going to happen, the reason why you're going to do this, there's this flaws to CTF I'm going to have you do. The first part of the CTF is you playing offense. You're going to basically try and do all the exploitation. The second part, the defender path, you're going to see how your actions ended up getting logged, and then you're going to do some forensic analysis using Athena, basically, to query out what are the sort of the suspicious accesses by sifting through the log files. And there's a whole bunch of jobs for doing that out there. I had a former student who was like, he liked to develop a lot, but then he liked security. And then he went out and he looked for all these different job opportunities. A whole bunch of them were just basically log analysis. So that's, if you like that kind of stuff, there's a lot of opportunity there. So you'll get to practice that in the defender path. Okay, this is a picture of what CloudTrail, so CloudWatch and CloudTrail are similar, but the idea of CloudTrail is to aggregate anything that's security related into a single service, and so you would have all of this stuff feeding into a single repository that you can then query to do the analysis of. Okay, there are a whole bunch of other services you can hook into, so logging is a service, the database stuff is a service. There are a bunch that the cloud class does, like the machine learning ones. The locations are services, searching, so YouTube search. And if you look at this graph, you see that the number of APIs that are available has just skyrocketed. So there is now this really robust API economy that is out there to monetize people's stuff. I've read an article, maybe I should share this. Wells Fargo, their API usage has basically gone through the roof. And you're like, Wells Fargo, what are they doing? But basically all of those apps on the front end, they're basically hitting APIs on the back end, implemented on cloud infrastructure. So that's what's going on. Okay, so that is an overview of the class. It's like a quick overview, but it's necessary in order for you to understand what you're going to do in the next couple of weeks. The next thing I want to talk about is navigating cloud projects, which is also a skill that you'll need to develop. And this is, I'm not going to be able to teach this to you in like, 10, 20 minutes I'm going to cover it. I'm just going to give you an overview of the kinds of things you'll be doing. And then the actual skill of developing it, you'll have to do using the exercises. Okay, so cloud projects are the first thing I want to talk about. These are sort of umbrella organizations that house all of a site's resources, right? Like you need something to isolate the resources of a project, and that's what the project abstraction is. And so a project has its own security and access control policies. It defines its own permissions and credentials. It has its own billing account usually, separates the amount of expenditures. And then it has a set of enabled services that project can access, okay? And the abstraction on Google Cloud is done with a project ID. So when you are accessing resources in Google Cloud, you'll come across the project ID identifier is typically used everywhere to identify which ID is associated with this resource. I have not ever seen the project number be used anywhere on the back end, so pretty much it's just the ID. So you should know your own project ID. On AWS, it's done with an account ID. This I do see everywhere in AWS. So this is a number associated with the entire project. Now for your accounts on AWS, you don't get that. Like basically Vocarium is the account ID, and then you don't get your own, I should say, because you're running your stuff through a sandbox. So you have Vocarium's account ID. If you own your own account ID, You can, because this is ornery, you don't really want people to say, this is my account ID, this is my access that I want to enable. Typically, you are allowed for an account ID to specify a alias. So in this case, this AWS PDX alias, this is the account that I'm using to run the Cloud Goat. I can just bind that to that account ID for people to log in. And this will come, we'll talk about this next week, actually, when we talk more about AWS. For both cloud providers, there's a notion of regions and zones. And these are areas in which you bring up infrastructure. So for Google and AWS, they both use this abstraction of, in terms of labeling the region. So US West 1, East 1, and Central 1. They're just different areas of the country. And then within each one of these regions, there are availability zones. And so availability zones are physically isolated sort of locations within that region. And they could be geographically located in the same place, but the idea is that the electrical sort of infrastructure and some of the building infrastructure is separate, so that if you have a fire in one zone, it doesn't affect the other zone. That's typically the differentiator. And so as an example, here are some availability zones, US West 1A, West 1B. And then if you look at what these mean in Google Cloud, you see that US West 1A and B are both in the DALs, but they have separate buildings with separate electrical sort of things, so that if a fire takes out US West 1A, US West 1B typically won't be taken out either, unless of course we get the big one, and then you'll wipe out the entire region. Okay, the other thing we'll need to talk about is how do you access stuff in the cloud? So both Google and AWS have the same figure, effectively the same. There's multiple ways of accessing cloud resources. The way that all of us are familiar with is the web console, right? You bring up the web UI, you log in, and you've got a bunch of different things you choose from. There's also the cloud shell, or basically the command line way of accessing resources, where it's like Unix commands, entering those things in. There's also support for programmatic access to cloud resources, so from Python. So say I want to launch a virtual machine from Python, both Google and AWS will give me libraries, packages for me to pip install and then just launch from my program. And then finally, Google at least has REST-based APIs. So if I just want to send a web request to launch infrastructure on my backend, I can just hit the REST API implementation. I don't see that as much on AWS, but I think AWS could easily implement that as well. Okay, so we're all familiar with the web UI for accessing cloud projects. So on the left is the Google UI. You'll eventually start navigating the AWS one more on the right. The CLI, so the command line interface, and this is sort of your Unix-like interface to your resources. On Google Cloud, there's a G-Cloud utility that basically runs all the commands, except for the ones related to things like storage. So the storage UI is using gsutil. On AWS, it's all AWS subcommand. So for example, on Google Cloud, if you want to list all your compute instances, it's gcloud compute instances list. And all of these are tab completion. So like when you're doing the Google Cloud exercise and you want to start typing commands, you can hit tab to figure out what the subcommands are. So definitely take advantage of that. On AWS, the AWS CLI does the same thing. The equivalent here is EC2 describe instances and run instances, and that's the equivalent to instances list and instances create. And so here's an example of accessing storage buckets, which you'll do a lot of. gsutil-ls lists all your buckets. gsutil-ls of a particular bucket, given a URI, lists that single bucket. And then you can create buckets using the gsutil-mb subcommand. And if you look over to the right, the gcloud UI is modeled after the way AWS did it, right? So AWS S3, LS, and those sorts of things. So these are typical command navigations that you'll be doing in your CTF exercises. Both of them have a hosted IDE that allows you to run the CLI directly without you having to install any software. So a lot of people doing Google Cloud love the Cloud Shell. And so if you bring up Cloud Shell with the Cloud Shell editor, you have a nice IDE in the browser, right? You don't have to install anything. You have in the browser the IDE on top, and then on the bottom your CLI, your G-Cloud CLI, for you to access the resources. AWS has this thing called Cloud9, which is the same thing. So you launch a Cloud9 instance, and then it'll bring this up. So you have the IDE, and then you can have a command line interface that has the AWS command. And then you can configure your credentials there. So those are two things that if you want to use, I'd recommend. I had a student last summer who was like, I don't like either of those, so I'm just going to run VS Code, and I'm going to install the G-Cloud SDK and the AWS SDK, and then I'm just going to go from there. So you can do that as well. You could basically do this locally with VS Code and then installing the SDK if you would like. But this is the option if you just want to run it within a browser. Okay, I mentioned that you can access the backend resources using Python. So here's an example for accessing Cloud Data Store. You would pip install the Google Cloud Data Store package, and then you can import it, and then you can create a client, and then go for it. On AWS, the Python package is Boto3, so you install it, and then you import it, and then you can get a database client. So these were the two serverless databases that we were talking about previously. Google also allows you to generate your own package dynamically using OpenAPI. So OpenAPI is this new way of you specify your REST API in a document, and then what you do is that you instantiate some client that will parse it and automatically generate the Python package for you, right? So this gives you Python packages for everything, which is what the OpenAPI standard is meant to do. And so this is Google API client or this discovery client is basically that part of Google's, where you're trying to instantiate on demand an API package that allows you to then execute the same commands that you would if it had been built into a regular package. Okay. There's also support for Ruby, Java, Go, and JavaScript for this. Okay, the last thing I want to talk about is access to the project using a REST API. And this is going to be specifically for the Thunder CTF exercise. There is this interactive API explorer that Google Cloud has. If you go to API Services Library, so we're going to try out the Compute Engine API, and you click on Try This API. So you'll get to this. If you look at the API library for Compute Engine, you can interact with the REST API for managing Compute Engine resources. So this is that fourth way of accessing clients, accessing cloud resources. So for example, if you go and you try and look at the API call for listing compute instances, you will see this in the documentation. You'll see that the REST API endpoint is defined right there. So this is the URI, and all you have to do is fill in the project and the zone, and you're good to go. You'll be able to list your instances. And then there's an Explorer window on this page, so you just fill that in. And then what you'll get back when you have well-formed that REST API, you execute it, and then you'll get back in JSON the result. And then you would parse that result to list your instances. And that's what the web UI does, actually. The web console, when you go and you click on your VM instances, is going and doing this, and then presenting a web UI on top of this data that it gets back on JSON. Questions about that? Okay. So that is it for the cloud overview. If there aren't any questions, I'm going to talk about vulnerabilities, which is more interesting. Okay, so let me